You have a brilliant idea for a new car component, and it's tempting to jump straight into your software and start generating glossy 3D models. But a design that looks right on a screen can still fail the moment it encounters real-world physics. Without consulting existing research, you are guessing at the stresses your part will actually face. The literature review sets the physical and regulatory boundaries for the entire project. It identifies the safety constraints, the environmental targets, and the strict material limits, all discovered through decades of industry testing. Relying on these peer-reviewed datasets is the only way to ensure an aesthetic concept can withstand the forces it will encounter on the road. Automakers operate under global regulatory mandates to reduce greenhouse gas emissions and improve the fuel economy of every vehicle in their fleet. This chart illustrates the direct mathematical relationship between mass and energy consumption. Reducing vehicle weight by 10% increases fuel efficiency by 5 to 7%. Swapping traditional steel for carbon fiber reinforced polymers eliminates up to 60% of weight while maintaining strength. Research also highlights natural fiber composites, like hemp or jute, as a way to lower the carbon footprint of the manufacturing process without compromising structural integrity. Analyzing these material properties allows you to solve for both weight and environmental impact before a single physical prototype is built. Out on the road, automotive parts face constant, repetitive stress. Engine vibrations and rough pavement deliver thousands of micro-impacts every hour a car is in motion. These cyclic loads determine the fatigue life of the part. Most mechanical components do not break from one large force. They fail because repetitive, low-level loads slowly weaken the material. Stress concentrates at specific points in the geometry. Over time, microscopic cracks form at these high-stress nodes and propagate through the structure until it snaps. This 3D suspension arm is analyzed with finite element analysis. The heat map shows stress concentrating at the sharpest joints. Armed with this data, engineers round out sharp corners to diffuse stress and extend the part's operational lifespan. Using these fatigue models allows engineers to prevent sudden, catastrophic fractures that could otherwise occur years after a vehicle is purchased. The most extreme test for any component is a high-speed collision, where the vehicle must protect the occupants from massive amounts of kinetic energy. Performance in these moments is governed by strict legal requirements, such as the Federal Motor Vehicle Safety Standards and NCAP ratings. Different materials react differently to impact. While steel is designed to fold progressively, an incorrectly engineered composite might shatter, failing to absorb the energy of the crash. This schematic shows a crumple zone in action. By researching material deformation, engineers ensure the car's front end collapses in a controlled manner, trapping kinetic energy. This dissipates the impact force before it reaches the rigid passenger cabin, keeping occupants safe. Ignoring these crash dynamics during the research phase leads to failed regulatory tests, safety risks, and the massive financial cost of a complete redesign. These trials show that effective engineering happens before the CAD software is even opened. Success depends on the empirical data gathered at the very beginning. Calculating environmental impacts, mapping fatigue life, and adhering to safety standards ensures the component meets every technical and legal requirement for the road. Data dictates the geometry and material of the final part, moving a design from a digital concept to a compliant physical reality.